Hello, good morning, everybody. Sorry I'm a bit late. I spent more time in my previous class than what I intended. So, how was your weekend? I hope you had a good one, especially because you had the exam over the weekend. How was it? Oh, it's nice to hear that, Fatuma. Is that your weekend or does that include your exam? Hopefully that includes your exam. Oh, hold on. Do you just see a blank on just a blank on my screen? Oh, nice to hear that. Also, Christina, yeah. Oh, I don't know why. Let me just restart this. Okay. Hmm, that's odd. Let me try it again. Okay. Yeah, how about the others? Because I know that you're right. There's only one FRQ question, but it has four parts. So actually we started grading it, or we were given the grading assignments for test three, and the deadline for us to finish it would be later tonight. So hopefully by tomorrow or day after next, you're gonna see your scores in the FRQ part. It's worth 40 points, I think. So yeah, hopefully by tomorrow you'll know your scores already. Uh, Though I haven't started grading my share, I'll do it after our class. I have 97 papers to grade. Hopefully, I'll finish it this afternoon. But anyway, based on the reaction of students, it seems that they found it easier than what they expected. So hopefully, it's a lot easier to grade. But let's see. Okay. Now let's continue our discussion about some problems involving section 9.1 and 9.2. So we started last time talking about sequences, and we said that these are just functions whose domain is the set of natural numbers. There are several ways of writing a sequence. You can write it as an ordered list of numbers, or using a formula, an explicit formula telling us how to compute the n term, or the formula could be recursive in nature, where we need to use previous values in order to know the n term of the sequence, all right? And I also think we also started talking about lower bounds and upper bounds for sequences. And let's see, are there some interesting problems here? Yeah, let's see problem 11 or set 11. Okay. So what would be the LUB and the GLB for this problem? Just as a quick review. Remember that the least upper bound, as the name implies, that's the smallest upper bound, and the greatest lower bound is just it, the greatest lower bound. I don't know, the terms are easy to remember, but sometimes computing them might be difficult. All right, the least upper bound, oh, maybe Fatuma, you're referring to 1.9 as the greatest lower bound, right? Because 1.9 is a lower bound because 1.9 is smaller than or equal to everything in the set. So it qualifies as a lower bound. And it is the largest or the greatest lower bound because if you go slightly to the right of 1.9, that will not be a lower bound anymore, right? So it's indeed the greatest lower bound. How about the least upper bound? So I know 5 is an upper bound, right? Because 5 is larger than everything that is contained in the set, assuming that the pattern holds, right? 10 is another upper bound. 10 million is another upper bound because 10 million is definitely larger than everything in the set. But what is the least upper bound? Meaning a number that is an upper bound, and if you go slightly to the left of that number, it won't be an upper bound anymore. Okay, so it will require you to have a knowledge or have an idea of how the pattern goes. So it seems that the first term has one nine, a single nine after the decimal point. The second term has two nines after the decimal point. The third number has three nines after the decimal point. The fourth term has four nines after the decimal point. So if you're looking at the 10th term, it will be 1 point followed by 10 nines, right? So what will happen for, what would be a least upper bound for this? Can you think of a number that is larger than everything in the set, but if you go slightly to the left of that number, it won't be an upper bound anymore? Well, Fatuma, you said it's 1 point, followed by how many nines? 1, 2, 3, 4, 5, followed by 5 nines. Yeah, how about, but the sixth term in the sequence will be 1 followed by 6 nines, which is larger than your 1.9999. So your 1.99999 is not an upper bound because it is smaller than 1 point followed by 10 nines, for instance. So it's not an upper bound. Okay, Fatuma, you said 5. 5 is an, sorry, no, you answered my previous question. Any other guess? What would be the least upper bound here? Remember, an upper bound must be larger than everything in the set, but if you go slightly to the right, it won't be an upper bound anymore. Christina, you're correct. The least upper bound here is 2. Because definitely, if the pattern goes on, 2 would be larger than everything inside the set. But if you go slightly to the left of 2, then it won't be an upper bound anymore, right? Because the elements in the tail end of this sequence has so many nines in them, all right? And I don't know if you remember from your algebra that 1.9 bar is equal to 2. Do you guys know what the bar means here? If you have a bar over a number or a string of numbers after the decimal point. Yeah, Fatuma and Christina, you're both correct. That means that that is an infinite number of nines. So it's 1.999 that goes on forever, right? And 1 point followed by infinitely many nines is equal to 2. And that seems to be the case here, right? So basically 2 is only achieved if you have 1 point followed by infinitely many nines. And so if you pick a number that is slightly to the left of 2, it won't be an upper bound anymore, because you can write a sufficient number of nines after the decimal point to be larger than that number that is slightly to the left of 2. All right. When I was in high school, or even in my freshman year in college, I cannot accept this fact that 2 is equal to 1 point followed by infinitely many nines. Because I'm thinking there is just an infinitely many number of nines. How could that be equal to 2? But it turns out that is indeed equal to 2. And now I agree that 1.9 bar is equal to 2. All right. Let's see this one. That's right. Set number 12. Set of all x's such that ln x is less than 0. Let's look for its GLB and its LUB. Okay. Now, any guess what would be the GLB? Let's do GLB first. Could you give me the greatest lower bound for the set of all x's whose ln is less than 0? Okay, there are some instances wherein looking for the GLB and the LUB might be difficult, so maybe you can try to rewrite the set into into an easier representation, right? So let's try problems 12 and 14, and I'm gonna do it. I'm gonna include the detailed solution. So let me just cut this and then copy this one. Let's do it in a new page. See below. Okay. So this is from section 9.1. Okay, let's try this. So for instance, for problem 12, okay, if you look at the set of all x's such that ln x is less than 0, let's try to write it in a more familiar form, right? It will be great if there's an interval notation for this set, because if you have an interval, if your set is given in terms of an interval, then it's much easier to find the GLB and the LUB, right? So, but let's us recall how the ln looks like. The graph of the ln function, or the natural log looks like this, right? And then our set would be the set of all x's whose ln is less than 0. And ln is less than 0 over this interval, right? So here is where the natural log is negative. So basically, we're looking at this axis. Okay. So the set of all x's such that ln x is less than 0 is this green region here, or the green interval here, right? Because if your x resides inside this green interval, then if you compute its ln, you will be below the x-axis. All right. So what will this interval be? Hint. Oops, what happened? It would be an open interval. What would that open interval be? Oh, first, do you agree that this set is indeed the interval shaded green here? Come on, guys, are you still with me? Okay, great, Fatuma. Then what do you think is that interval? I guess the left bound is obvious, right? Because the left bound should be equal to 0, right? Because ln's are defined only for positive numbers. So you start at 0. And then, Christina, you're correct. It's 0 to 1. Because remember, ln of 1 is equal to 0. So here, that's x equals 1. Right? So basically, this set would be just the open interval 0, 1. And since it's the open interval 0, 1, it's easy to see that the GLB is 0 and the LUB is equal to 1. Right? Okay. Let's try 14. Set of all x's such that x minus 4 is greater than 2. Okay, so the set is not easy to interpret. Actually, you can interpret this. You can interpret it as the distance, because here this would be the distance between x and 4, right? So you're saying this would be the set of all x's whose distance away from 4 is larger than 2, right? But it's still, I guess, easier to find the GLB and the LUB if they exist, if you will look at this in terms of an interval, right? So let's solve this inequality. Just to remind you that here again, we need some topic or some concepts from algebra, right? So we have an absolute value inequality here. So that means in order to get rid of the absolute value, we need to take a look at what is the inequality involved. The inequality involved is greater than, right? So that means this will be divided into two cases. It's either x minus 4 is greater than 2, or x minus 4 is less than negative 2. And then we solve each inequality. So first, I add 4 to both sides. So here I'll get x greater than 6. Or here I'll have x less than 2. Right? So basically, if we will plot this, the x's that belong to the set will be those x's that is either greater than 6 or less than 2. So basically, this set would be this x's, right? So this would be negative infinity to 2 union 6 to positive infinity. And does this set has a GLB and an LUB? What do you think, guys? Okay, Christina, you're correct. There is no LUB and no GLB as well, right? Because in the first place, this doesn't have a lower bound, right? Because for a lower bound to exist, that lower bound must be smaller than everything in the set. Unfortunately here, the set extends indefinitely to the left, so we cannot find a lower bound. If you don't have a lower bound, then it's impossible to have a greatest lower bound. In the same fashion, the graph extends or the set extends indefinitely to the right, so we cannot find an upper bound. Okay, and since we cannot find an upper bound, then there cannot be a least upper bound. So this is there is no GLB nor an LUB because this set is unbounded, right? Okay. Now, yeah, so you need to recall how to compute absolute value inequalities like this. Let me go problem 15. Let's see. Yeah, I remember problem 15 is also interesting. Okay. Again, if you see an algebraic definition for the set, maybe it would be better to look at it as an inequality and write it as an interval if possible. So for this case, I will solve the inequality x squared minus 2x plus 1 less than or equal to 4. But I'll notice that the left side can be factored. In fact, it is a what? It is a perfect square trinomial. It is x minus 1 quantity squared less than or equal to 4, right? And then I'll take the square root of both sides, but be careful when you take the square root of x minus 4, of x minus 1 squared, you write it as x minus 1 inside absolute value symbols, and this is less than or equal to 4. And then if you have an absolute value less than or equal to a number, then it will be translated into a continued inequality. So this would be x minus 1 between negative 4 and 4. And then we solve the inequality, right, by adding 1 to all sides. So I'll have negative 3 less than or equal to x less than or equal to 5. So basically, this set looks like this. X's between negative 3 and 5, the bounds are included, so this would be this set. So this set is nothing more but the closed interval negative 3 to 5. And so it's easy to see that the greatest lower bound is negative 3, and the least upper bound is positive 5. Is that good? Is that clear, guys? Okay, so this is just a reminder that you need to at least remember how to solve inequalities like the basic ones. So try to review your algebra notes. Okay. Any other question in 9.1? I guess the gist of section 9.1 is finding the LUB and the GLB because they imply some properties about the convergence of sequences, right? So any questions on that before we go to section 9.2? Because I think section 9.2 is the more interesting one, wherein we need to determine whether a function is indeed or a sequence is convergent or not. Okay, great. So let's go to the next section, which is about convergence of sequences, right? So in a nutshell, a sequence is convergent if the terms in the tail end of the sequence approach a certain number. Though there is no tail end because the sequence is an infinite list, right? But what I'm trying to say is that if as the index increases, those numbers in the I'm again about to use the term towards the tail end, but essentially, if you have a sequence A1, A2, A3, and so on, if the terms here approach a certain number, right? And that's when we say the sequence is convergent. So as the index increases or the subscript increases, you will see that it will be convergent if they approach a certain number. If they won't approach a certain number, then the sequence is not convergent, or we say the sequence is divergent, right? And some notations here to signify, oh, basically we're just taking a look at it and seeing what will happen when n approaches infinity. So remember, we can write it as a sub n, right? So we are just looking for what is, or what will happen to an as n approaches positive infinity. If this is a number L, then sequence is convergent. Otherwise, if there is no such L, if you cannot find a real number L to which the terms of the sequence approach as n approaches infinity, then we say that the sequence is divergent. So there are two ways how to determine whether a sequence is convergent or not. Number one, by an intuitive observation of how the elements of the sequence look like. So you just imagine or you just analyze what will happen when n approaches infinity. Sometimes you can do it by visual inspection. That is fine. Or sometimes it would be helpful to use the hitch theorem or the hitching property of sequences. So I can let f be the real valued function analog of an. Meaning, remember, an or sequences, these are functions whose domain is a set of natural numbers. But if you will extend the domain and allow any real number to be part of the domain, then the limit of the sequence an will be the same as the limit of f of x as x approaches positive infinity. You might think there's no big difference between the left and the right-hand side, but there are some technical nitty-gritties here. Remember, an has domain the set of natural numbers. While here, I'm considering f to be the extension of an, so that any real number, at least any positive real number, will have an image under the sequence. So basically, if you want to see an illustration, I guess last time I told you that the graph of a sequence is just a bunch of points, right? Because the domain will just be the set of natural numbers, 1, 2, 3, 4, 5, and so on, right? And you cannot connect the dots, because if you connect the dots, then you will say that there is a function value between, or for x's between 1 and 2, which is non-existent for sequences. But if you will look at f, what is f? F is the real valued function analog of an. So if I will connect the dots, this will not be an anymore, but this is f of x. So f of x is the continuous function. An would be the sequence, which would be just the black bunch of dots in here. But you will see that if they are really analogs of each other, then what happens to f when x approaches infinity is the same thing that will happen to an as n approaches infinity, right? At least I hope graphically you are convinced with this argument. So instead of looking at what will happen in the long run to the list of elements I have, what I'll do is to compute for the limit of the real valued function analog of an. And what's the advantage of doing so? Well, we can use the techniques we learned in Cal 1. We can use L'Hopital's rule. We can use all of those things that we have done for evaluating limits. And that's one powerful tool that I can use to determine whether a sequence is convergent or not. Okay, now perhaps let me show you some examples or some elementary examples here. Let's say determine whether the following sequences converges. Number 1, let's see. Let's have 1, 1, 1, 1, and so on. Is this convergent or divergent? Maybe let's add something here. If it converges, then find the limit. Okay, do you think this sequence converges? And if it does, then to what number? Okay, great, Christina. Yes, this converges to 1. Okay, because remember, the limit of a sequence is what happens in the long run. Here, I just have a bunch of 1s. So when n becomes very, very large, I expect that the value at the end is also equal to 1. So basically, you're just imagining what will happen at infinity, or what happens in the tail end of the sequence. So great, it's convergent to 1. How about this? Convergent or divergent? Okay, if you want, you can unmute yourselves if it's easier to answer orally. Okay, it's convergent. Convergent to what? Converges to 0. Correct, Christina and Fatuma. So there are 2 ways. Number 1, you can just imagine what happens. So this is 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, and so on. So in the long run, the denominators become very, very large, right? So that means you have 1, which is the common numerator for everything, divided by a very large number in the tail end of the list, it will go to 0. That's fine. You don't need a hand solution for this. But if you are more of an analytic or a visual person, you might want to say, okay, here, an is equal to 1/n, right? And if I want to get the limit of an as n approaches infinity, this is the limit of 1/n as n approaches infinity. I'm going to use the Hitch theorem and use the techniques I learned in Cal 1, how to evaluate the limit of 1/x as x approaches infinity. This is 1/infinity. 1 divided by a large number, this will go to 0. That's how you can solve it analytically. All right. Let's try problem 3. -1 to the power n. So I hope it is clear that this is divergent. Because if you take the limit of -1 to the power x when x approaches infinity, it won't exist, right? Or you can do a visual inspection and see how the sequence look like. So the sequence will be the sequence -1 followed by a 1, -1, 1, -1, and so on. So basically, the pattern seems that it will just be alternating between +1 and -1. And towards the tail end of the sequence, I don't know where am I going. Am I going to +1 or am I going to -1? And it's impossible to determine that, right? So that means there is no limit for this sequence, so it is divergent. Because in the long run, it's a toss-up between -1 and +1, because this will just oscillate forever. All right? How about this? Let's say, let's say we have 1, -1/2, 1/3, -1/4, +1/5, -1/6, and so on. So is it convergent or is it divergent? Or probably, if you want, we can write it as what? -1 to the power n plus 1 all over n. So take your pick, analyze it using a list or using a formula for the n term. Will it be convergent or divergent? Okay, anybody? Okay, Christina said it's convergent. Convergent to what? Right, it's correct. It will converge to 0. Oops. Well, 2 ways to answer this. Solution 1, do an intuitive analysis of the list. So we start at 1. That's the first element. That's A1. And then we'll go to -1/2. That's our A2. A3 is a third. Say A3 is here. And then A4 is -1/4. And then A5 is 1/5. And I hope you can imagine what will happen. A6 will be here. A7 will be here. A8 will be there, and so on, right? So as the index increases, the values seem to be very, very close to 0, even if they are alternating in sign. But in the long run, even if they alternate between a positive and a negative number, they will eventually converge to 0. All right. So this will go to 0. Good. All right. So it doesn't matter if it's it is not automatic that if you have an alternating sign that it is automatically divergent, right? There are some alternating sequences that converges. Okay, let's see. Or you can do another solution. Do it analytically. So look at the limit of -1 to the n plus 1 all over n as n approaches infinity. And look what happens. Well, the numerator, when n goes very, very large, it's still a toss-up between plus or -1, right? So the numerator is either positive or -1. But the denominator, as n goes to infinity, is a large number. So basically, you have plus or -1 divided by a very large number. It doesn't matter if it's +1 or is it -1. The quotient will still go to 0, right? So that's why you can say, oh, the limit is equal to 0. Thereby, it converges to 0. Okay. Let's try one more. Let's say n minus 6 to the negative 1 to the n all over n. Okay, try this one. I'll give you a minute to analyze this problem. And please tell me, anybody can tell me on the chat or orally, will this converge or diverge? Okay, anybody? Fatuma said it's divergent. Do you guys agree? Anyone who has a different answer? Any other guess? 5, 4, 3, 2, 1. No other guess. Okay. Actually, I think this is convergent. Oh, Fatuma, why the change of heart? Where do you think will it converge? Your second answer is correct. It is convergent. Why? Well, I'll do it analytically. So I'll take the limit of this guy as n approaches infinity. Yeah, Christina, it's almost like the other one, right? But here I can say, I can simplify it first. So I can do the division term by term, right? So n divided by n, that would be 1, minus, I'll divide these two guys, but that will still be 6, negative 1 to the n, all over n, and take the limit as n approaches infinity. Well, we have seen that this type of sequence will go to 0, right? Because the numerator in the long run is either plus or minus 6. But the denominator becomes very, very large. So it's plus or minus 6 divided by a large number. This will go to 0. So essentially, this would be 1 minus 0. And the limit is 1. And you're correct, Fatuma, right? So this converges to 1. All right. Oh, let's try one more. Let's see. Let's try 3n squared plus 4n minus 3 all over 4n cubed minus 3n plus 1 over n. Okay, convergent or divergent? Fatuma, they are convergent because there is a limit. But the limit can be any other number aside from 1 or 0. As long as you get a number as the limit, then it would be convergent. It doesn't have to be 1 or 0. It's just that my examples always converge to 1 or 0. But I'll give you one later that will not converge to either 1 or 0. Oh, Christina, you're correct. This converges to 0. How did you get that? How do you come up with that conclusion? Right, so you can, Christina, that's a good approach. So you can look at the exponents on top and bottom, which should remind us of how to evaluate limits at infinity, right? So remember, we're looking for the limit of the sequence as n approaches infinity. And then I can use the Hitch theorem and just replace all the variables by x. Well, it seems that the change in the variable here is nothing but a superficial change, but I'm doing the change just to signify that this one is a sequence because the variable n, only takes natural numbers as values, but here x can be any real number. Okay, because here, if you remember from Cal 1, if the degree of the numerator, is smaller than the degree in the bottom, I think you had the expression bobo bottom before. So here, if you take the limit, it will be equal to 0 because the exponent in the denominator is larger than the numerator. Okay? Or another way of looking at it, if you forgot that acronym already, what you can do is to, instead of using the H theorem, another way to do it is to simply analyze what's the behavior of the function. So you can say, okay, I'm going to stick with the limit, with the sequence. But if you look at the numerator, when n increases, -3 becomes insignificant, right? It doesn't have a big contribution whenever n is very, very large. The same goes for n. For n, even if it will be a very large number when n approaches infinity, it will be overshadowed by 3n squared. So you can say, oh, the numerator in the long run, or for large n's, will only behave like 3n squared. All the lower terms can be ignored. Because n goes to infinity, there is a sufficiently large n that 4n is insignificant compared to 3n squared. And similarly, in the long run, the denominator will just behave like 4n cubed. And then we can cancel some of the n's. So this will be 3 over 4n as n approaches infinity. But here you have a constant 3 on top, but you have a something that goes to infinity in the denominator. So this will definitely go to 0. Okay. So there are several ways on how to do it. So let's try this one. Sequence of, say, 4n cubed plus 3n minus cosine n all over -3n cubed plus e to the 1 over n. Okay, let's try problem 7. You have this sequence, which is a ratio of 2 expressions. Then what do you think? Will it converge or diverge? Okay, it will converge to what number? Great, Christina. It will converge to -4/3. Okay. Why? Let's see. Okay, you can do the same analysis I did before. And imagine n going to positive infinity. Well, if n goes to infinity, cosine n, we don't know the exact value of cosine n, but for sure, cosine will just be between -1 and +1, right? So this is a small number, cosine n, either plus or -1. So in the long run, it won't affect the sum in the numerator. The same as 3n. 3n will be overshadowed by 4n cubed. So the numerator only behaves like 4n cubed. All right. What happens to the denominator? In the denominator, when n goes to infinity, 1 over n goes to 0. E to the 0 is equal to 1. And in the long run, 1 is insignificant compared to -3n cubed. So that means the denominator only behaves like 3n cubed. Good. And so if you simplify the sequence, you can say that, oh, in the long run, it will just behave like -4/3 because the n cubes will cancel each other out. So the limit would be -4/3. So this converges to -4/3 because of that argument. All right. Any questions so far? Is everything clear? Or do you need some more time to digest this topic? I hope it's clear because it's sort of a review of what you did in Cal 1, finding limits at infinity. If you already forgot that, take a look back at your notes and see, and see what happens there. Probably final example for the day. Let's have, say, okay, let's try this one. The sequence is n over n minus 2 raised to the power n. So if you will list the elements, right? When n is 1, we'll have, oh, sorry, let's make it a plus, okay? So n over n plus 2 raised to the power n, when n is 1, we'll have 1/3. If n is 2, we'll get 2 over 4 squared. 2 over 4, or that's going to be 1/4, right? If n is 3, we'll have 3 over 5 to the third power, which is 27 over 125. And then when n is 4, we'll have 2/3 raised to the fourth, which is what? Or something. And if we do the listing, it doesn't seem obvious to what number will this, it is not obvious whether this will converge at all, right? Because the numerator changes because the numerator is 27. Then the next one would be 2 times 2. It's going to be 16. The denominator will be 3 to the fourth, and so on. So there would be variations both in the numerator and the denominator. So it's not clear whether this will converge to 0 or if it will converge at all, right? So I guess for examples like this, it's better to analyze it analytically. So we need to find the limit of n over n plus 2 raised to the power n as n approaches infinity. And then I guess here I need to use the Hitch theorem and replace the variables by a real variable. I need this because I am planning to use some of the tools that we learned in Cal 1. Remember Cal 1, all the functions there are functions of a real variable. Most of them are continuous, so we can apply some of the techniques that we learned about some properties about continuous functions that we learned. So, okay, so what will happen when x approaches infinity? Well, if you try direct substitution or analysis of, say, the base, when x approaches infinity, the base will go to 1 because it's linear, so it's 1 over 1, so the base goes to 1, but the exponent will go to infinity. And remember, 1 raised to infinity is an indeterminate form. So being an indeterminate form, I need to be a bit careful here. So I will let y be equal to x over x plus 2 raised to x. I hope this will ring some bells, right? So this is basically the technique that you have learned in Cal 1. There's an indeterminate form, but the cause of the indeterminacy is the exponent. So remember, when you have an indeterminate form caused by an exponent, we need to take the logarithm of both sides to get rid of the exponent, right? So I'll call y to be the argument inside the limit. I'll take the natural log of both sides, and then I'm going to use the property of natural logs. that says that this supposedly I'll have the power x inside the log, but thanks to loss of logarithms, this exponent can come down as a coefficient. That's why I have it here. And I'll take the limit, oops, as x approaches infinity. Okay, but if you'll take the limit as x approaches infinity of the right side, this would be infinity times ln of 1. But ln of 1 is 0, right? So it's an indeterminate form, infinity times 0. And I hope you still remember how to deal with limits of the form infinity times 0. Okay, so I'll give you a chance to take a look back at your notes in Cal 1. So try to answer this problem and let me know on Wednesday if you got the answer or if you got the solution for this one. I guess this is convergent, and my guess is that it will converge to E. Though I'm not sure if there's a constant somewhere, but I'm thinking this should converge to E raised to a constant. I'm not sure about what that constant is. So try to solve it, and then let's verify if indeed this will converge to E or to some other power of E. Okay. All right, so I guess this is a good time to stop. So I'll hope you guys will try to answer this one, or yeah, try to attempt this one. And let's start with this on Wednesday. Is that good? Okay, I hope it is. And then, yeah, let's stop here. Thank you for coming today, guys. And then we'll see each other again on Wednesday, hopefully with your answers to this one. Okay, bye, guys.